Welcome to Walkabout the Galaxy, the unpresumptive astronomy podcast where the science is universal, the opinions are personal, and the explanations make you go, okay.
Okay. Huh.
We are strange, charming down the astroquarks, also known as Josh Caldwell,
Addie Dove, and Audrey Martin.
Coming to you from the Walkabout studio at the University of Central Florida. Be sure to follow us on Instagram and anywhere else we may happen to show up, but mostly Instagram.
Mostly Instagram. Thanks, Audrey. Yeah.
Yeah.
I need to catch up.
Catch our videos on YouTube. We are at Walkabout the Galaxy. Our stumper today is about travel.
Okay.
What's your preferred mode, if you could have one of these?
Okay.
Hyperspace,
Ooh.
which is Star Wars.
Mm-hmm. Mm-hmm.
Warp drive, which is Star Trek.
Mm-hmm.
And then whatever it is that Captain Marvel does.
Oh, yeah.
Oh, like bloop, bloop.
I don't know. She's sort of like individually, personally
can some sort of special travel
through
space
the
and
universe,
time.
through the galaxy or something. So, but she can't like
take people
have a
with
ship
her.
That does that. So like she wouldn't be able to take all her stuff with her.
Yeah. Because she'll like pop in and out and be like, I'll see you soon.
Yeah.
You guys let me know when you're here. I'll be waiting.
Right.
Yeah, that is hard. But it would be nice to not have to go to a ship. Like to need a ship.
You just go.
So this is part of what makes it stumpery.
Yeah. My gut says Captain Marvel.
Captain Marvel?
Yeah.
Cool.
Yeah.
You want to just be able to like step outside and say, I'm out of here.
I don't even need to step outside.
Does she?
I feel like she usually steps outside.
Oh,
maybe it creates like some air.
I mean, please at least step outside so you don't put a hole in the ceiling.
Right.
Yeah.
Okay. Got it.
Even if you can punch through the ceiling.
Because it is some sort of like
it's kind of rude.
Physical transport. It's like a physical It's not like It's not like
she's not transporting like Star Trek transporter.
Right.
She's flying somewhere.
Yeah, like physically moving
she's
somehow
like
through
some
space
kind
and
of
time.
Superman
Doesn't
kind
really
of
make
motion.
sense.
Yeah.
Got it. I still want it.
Okay.
I don't.
You don't care?
No.
You don't want to travel?
You're
feel
giving
like
off an I don't really care vibe.
I feel like we know more from the extended Star Trek universe about how the Star Trek travel works
compared to hyperdrive or whatever.
Compared to how hyperdrives work, which is kind of like you hit it if it's not working, which is very classic any hardware.
Know you pull a lever and either it works or it goes.
You got a power toggle on or off, and then
sometimes it goes.
Yeah, and then it's not good. Then sometimes you need a special screwdriver to fix the thing, or R2D2 has got to fix the thing. Yeah.
R2 is going to show up in the trivia.
I love R2. I don't know. Star Trek.
Yeah, me too.
Well,
for most of the same reasons.
Yeah.
I want to have my stuff.
Yeah, that's fair.
You know,
and I hold something.
Yeah, well, okay. You're a more frugal person than I am, I guess.
Guess so.
Yeah.
I'll take that as a compliment.
Today, we'll talk about Polaris Dawn.
Yeah.
Some moon updates and some exoplanet super-Earth formation updates. But first, this episode of Walkabout the Galaxy is brought to you by planetary rings.
Oh, you like those.
Show your planet just how special it is with the timeless gift of a ring. Planetary rings are available in multiple sizes, compositions, and styles, including dusty, dense, icy, narrow, and broad. Visit our showroom at Saturn for examples of all types of planetary ring, including the braided F ring and sparkling G ring. Show off your style by embedding arcs or moonlets in your ring, and your planet will wear it proudly for tens of millions of years or more. No matter what size your planetary body is, Planetary Rings has a ring for you. Planetary rings may experience spreading, erosion, and darkening from impacts. Planetary rings should be kept within the Roche zone at all times. Planetary rings. When it's the real deal, it's made to last.
Zales.
K.
Very good. It is Zales.
Yo! Every kiss begins with K.
Yeah, but I thought maybe they had a different one.
Yeah, that's fair.
Yes. Frequently they have multiple, but well done. I couldn't believe that Planetary Rings had not sponsored the show, given the amount of times I've talked about Planetary Rings.
Yeah, maybe they felt like they didn't need to sponsor it. They got enough free press. They didn't need to sponsor.
We haven't talked about them recently, and so they got to dish out some cash.
Yeah. So, space news.
Space news. The big
Polaris
news from
Dawn.
today.
Yeah.
Hot off the launch pad is Polaris Dawn launched this morning.
In the wee hours.
In the wee hours. It was a little
dawn.
less wee.
Pre-dawn.
It was just pre-dawn. It was 5 something.
How's it going so far?
It's okay.
Hey, that's good.
So this is a SpaceX rocket with a special Crew Dragon capsule that is got a crew of 4 people who are just paid for the flight.
They did.
Or one of them paid for it.
They are private
astronauts.
So, at least one of them paid for the flight.
Right.
Yeah, so Jared Isaacman is the commander of the mission. What word? And he probably paid for all of it. And he is sponsored the Polaris program. He was also the one who flew with the Inspiration 4 crew that flew a while back. That was one of the first private astronaut missions with SpaceX. And the Polaris Dawn is super exciting. It's the first of maybe 3 sets of missions. This one has these sort of crazy things where they're going to a really high altitude in one of their early orbits. So they're going to go out just sort of into the inner Van Allen radiation belt.
Yeah.
Right.
It's like just past the edge of like the radiation belt and then come back. And they only do like I think they only do basically one orbit that high, and then they sort of come back into a more stable orbit.
Okay.
And then they settle into in a lower orbit that's still pretty high. That's like 700 kilometers.
Right.
Which is higher than the ISS.
Right.
And they're going to, at some point in a couple days, so they've already started the depressurization of the spacecraft, I think, because they're going to do an EVA, a spacewalk, in a few days.
Right.
So this should, in theory, all happen before we record again and before the next episode comes out.
Right. And
because it's only like a 5-day mission.
And these people paid for this.
well, one
person
of them
did.
paid
One
for
person.
And
it.
2 of them are
okay.
SpaceX employees, which is pretty interesting. They're both like pretty high on like astronaut operations for SpaceX.
Well, that makes sense.
And they're like have engineering backgrounds.
So they're gonna the tippy tip of the Crew Dragon, where normally it would dock to the ISS, is opens up. Then, as we discussed before, the whole capsule is exposed to the vacuum of space. Right. So they're all going to have their spacesuits on when it opens up.
And these
There's
are new
no airlock.
spacesuits as well.
Yeah, they're a new design of a spacesuit.
And then they'll be tethered to a ring, and they'll sort of like poke their heads out and kind of like not really go.
They're not going to like free float.
Anywhere.
They're going to be holding on to things the whole time.
And tethered to things, right?
And tethered.
Okay.
And like it's interesting because like the graphics I've seen sort of shows like handrails.
Yeah.
And I'm like, did they install that? Do those pop up? Do they install those? Like, how does that work? So I don't know. I think it must pop up out of the inside or something.
Yeah.
But it'll be interesting.
It's a nail biter.
Yeah. I have a feeling it's they'll sort of be doing what like I do on any boat, which is holding on really tightly, just sort of cautiously peering over the edge.
Say you did it. And there's 2 people who are supposed to go actually step. I don't know why all 4 aren't, but 2 of them
Just
are going to
like
actually
drift
go
out.
out and come back in.
So if the depressurization is starting, does that mean they're in their spacesuits and they're going to have to stay in their spacesuits the whole time?
No. So like when the crews on the space station are going to do a spacewalk, they go into the airlock, usually a number of hours before the spacewalk. And they go into an airlock space. And that airlock space is the only thing on the ISS that gets set to like a different oxygen ratio, like a different mix of breathing air that has a different partial pressure and then also a lower pressure. And so they start to do that. And it's like when you go diving, you don't want to get the bends. So you have to like work on where the bubbles and like chemistry is of your blood and your air in your system. And so they do that. And so I don't think they're in their suits.
Adapted. They're getting sort of pre-adapted their blood gas levels.
Cool.
It's a complicated thing, that whole business.
Yeah, it does sound really complicated, especially if all of them have to go through all of it. But
Fingers
so
crossed.
a 5-day mission, then they're landing in the water.
Somewhere
they're
around Florida.
in the ocean.
Yeah, they'll water
off the
down.
coast of Florida.
Splash down somewhere around Florida, which hopefully we don't have another tropical storm at that point.
Right, because there actually is a tropical storm in the Gulf of Mexico at the
currently,
moment.
And then there's a couple other X's over in
on the way. Yeah,
it's always exciting for me when my hobbies of watching the hurricane map and watching launch windows.
Well, and this one was delayed because of
part of it was
forecasts
because of weather.
for the splashdown.
Yep.
So it's kind of surprising that they went.
I know.
Yeah. They're going to thread the needle between a couple of hurricanes, I guess.
They did for the launch, so.
Yeah.
So it's exciting. Hopefully they'll get lots of cool data.
Yeah.
And then
it'll be as you mentioned, it's a higher orbit than the space station. we use the term LEO or low Earth orbit a lot, which is just what it describes. And the altitude of the space station, 500 kilometers or so altitude, or 450, a little bit less than 300 miles or so. And so they're going considerably higher than that. Still, what would be classified as low Earth orbit, so it's inside most of the magnetosphere. Examples of things that are not low Earth orbit would be communication satellites, which are geosynchronous orbit or GEO, and they're 20-some thousand kilometers altitude. So very, very different realm, much, much higher altitude. And then, of course, a long time ago, astronauts went to the moon. But since that time, since the moon missions of the Apollo program, these will be the highest above the surface of the Earth.
Oh, I didn't realize that.
I mean,
that's pretty significant. That's like,
I mean, it's higher by like a factor of 50% or maybe a factor of 2 at most, or not quite a factor of 2 compared to a factor of whatever, hundreds or thousands if you're talking about getting to the moon. So
I hope they share their data. Since it's a private company, they don't it's not like NASA where the data eventually has
and
to.
Most of the data is being
publicized.
collected by if you look at the website, there's all their sponsors and things like that.
Yeah,
so a lot
that's
of
what I was
data is
just
being
looking
collected
at.
by companies. They have these weird fitted ocular pieces, like an eye, like a weird contact that takes data or does something. I don't
astronauts
know.
are
Yeah.
wearing something?
In one of the pictures, they all look super creepy because one of their eyes is extra shiny.
Oh, wow.
I really don't like that picture. But yeah,
Wow.
that thing.
Oh.
Click on that picture. I think they're
Interesting.
all wearing it in that picture. Oh yeah. Anyway, some of it's all very future. It's all very interesting. Jared Isaacman, as Elon Musk, has ideas about how we can more quickly move forward to space exploration for more people. So he's got a bunch of money from.
Yeah. It's still super expensive.
Yeah.
And it's still not the easiest place to live. Right. So one thing that's important to remember is even if we could just go to Mars just like that, it's a lot worse off than the Earth is.
It's sponsored by St. Jude's Children's Research. This is a little off topic, but I'm very confused by that.
So they donate a ton of money to St. Jude's as part of it. They do a bunch of fundraising during the flight, and they sell things afterwards, and they donate. They did this with Inspiration 4 too.
It's a partnership.
Okay. So it's
one of the
not
people
like
who
St. Jude's is financing it.
No.
That's how I read it. And I was
I know.
this makes no sense at all.
No, so you can donate to St. Jude's, and the
Got
first
it.
flight, the Inspiration 4 flight, one of the people who flew, she's a big space communicator person, but she also had been a St. Jude's patient when she was little. So
Yeah.
it's
Got
pretty
it.
that partnership is super cool.
That's nice then. Okay.
Yeah. Speaking of the moon, I did speak of the moon.
We did.
And going there.
There's recently been announced, this is a segue to our science topics, is the last week maybe 2 weeks ago,
I don't know time.
they announced the selection of intuitive machines for another lunar landing mission. So this is for the CP-22. So this is Eclipse Payload 22 mission. There's a lot of acronyms. Anyway, this is the mission. One of the instruments is the same one that got selected when our PRISM payload got selected. So we're CP-21 and they're CP-22. So their mission got selected, and there's a bunch of other cool payloads, including L-Cirrus that carries on, and some others.
There was so many different letters in there. I kind of lost it.
It doesn't matter. So this is a lunar lander that's going to a south polar region. It's going to have a bunch of cool instruments on board. They just selected Intuitive Machines to do the landing.
And who are Intuitive Machines?
It's one of the companies that's building lunar landers.
Okay.
So IM-1 was the one that
part of the new space economy.
IM-1 is the one that launched and had.
And made it to the surface.
Did it make it, or did it have a problem?
I thought it made it to the surface, but it used backup cameras.
It sort of toppled over. It didn't have good comms. It got some data from most of the instruments.
Right.
But it wasn't a super successful mission.
It kind of did a faceplant.
Yeah.
Is that one?
IM is also the company that's supposed to provide the vehicle for the Viper mission. That's not happening, maybe, or is happening. And they have a bunch of different landers. Anyway, it's exciting. They got selected
to
go in 2020. 2025 or 6.
That's before
2026. They're before us. Yep.
Even though they're 2 in
Yeah,
year
the
1,
naming's
or they're
dumb.
22 and you're 21 or something.
That means that we'll be selected soon.
Okay.
Ooh, yay.
All right. And by we'll be
I
selected
mean,
soon,
the
what you
lander
mean
and
is
rover provider
the
for our mission will be
spacecraft
selected
that
soon.
carries your scientific instruments, which have already been selected
Yes.
for the Lunarvise mission, will be selected. So you'll know your ride.
Yes.
Right.
Which
So
is
you're kind of
exciting.
like waiting for your Uber.
I am.
You're there.
We don't know who our driver's
You've
gonna
been there
be.
for ages. You've been saying, okay, we're going to get you an Uber to the moon. And you've been like waiting
Where's
for the
my-
driver,
yeah.
and then you're
It
going to
hasn't
get it.
updated who it's going to be yet.
I see.
So,
Okay.
yep.
All right. So, what are some of the interesting things about the moon that we hope to learn more about with this upcoming mission?
Another recent mission.
Yeah, another recent mission was the Chang'e 5 mission that China sent. They sent a lander and a rover both and collected some sample and then brought that sample back to Earth.
Okay. How much?
1.7 grams.
Okay.
So a very, very, very small amount.
That is.
But
That's like smaller than a multivitamin.
yeah, that's not how I would have thought about it.
How
but
would
yeah.
you have thought about it?
I don't know.
Okay. Well, there you go.
Yeah.
I think I win that
think you
particular
do win
exchange.
that one.
How big is a typical multivitamin?
Yeah,
They're-
how many grams?
They're ginormous.
But like how many grams? Like
How many
2?
grams?
4?
Wow.
But okay,
Maybe I
so
don't
there was like 1.7 grams, which is very little, but there were a whole bunch of particles within this 1.7 grams, and like 3 particles that were like,
Tiny.
just the tiniest of things. They found to be volcanic in origin. So like volcanoes,
Okay.
even
So
on Earth,
these are little grains.
Are they glass beads?
they're glass beads.
Okay, but can't glass beads be created by impact shock?
Yeah, and so that is the part of this that I don't fully understand. So, because in this article, they do talk about how impacts can create glass beads. I think the morphology of the bead, so like how it's shaped, is different. I think you get more beads like stuck together whenever there's an impact, but I'm not 100% sure on that.
Okay.
So I don't know.
You're
But
waving your hands a little bit, but that's okay.
Yeah.
So
they
from the composition and the nature of these glassy beads and their morphology,
Yeah.
they're like, these is not impact shock melt.
Right, yeah.
Impact melt.
Yeah,
what is
exactly.
sometimes
Yeah.
called,
So they say this
is
isn't
volcanic.
Yeah, it's volcanic. And so then they did some radioisotope dating using the uranium in the glass beads and found that it was like 125 million years old, which
What?
sounds really old.
Not when you're talking about the moon.
Now
it
we're
doesn't.
Exactly.
talking about the moon.
Yeah. And so that is way more recent than any well-known
That's crazy.
estimations. But they link it to IMPs. IMPs are, what does IMP stand
Irregular
for?
Mare patches.
Yeah, irregular Mare patches. Duh. Which I think is the target site for another
The third
Eclipse
prism mission.
Yeah.
Irregular Mare patches.
Yeah. And they're
That
like,
sounds like, something you get on your skin.
Yeah.
it kind of looks like it too.
does.
Okay.
It looks like a rash, but
does.
like
I might
It's
have to
not-
see. I'm seeing the doctor in a couple weeks, and
Might
I'll
ask if you have
ask
any
about some
irregular Mare
Mare
patches.
patches.
have any
Yeah.
imps?
Maybe some
Dermatologist.
topical ointment for irregular Mare patches could sponsor the podcast.
Oh yeah, that would be good. But yeah, so these imps are still not really known. It's not known like what their origin is, but there aren't
So-
that many craters on them, and so
What is it that makes them irregular?
they have rough surfaces.
They're just not very regular.
Yeah, they're just like really
Yeah, so imps are
regular.
What makes the irregular Mare patches irregular?
they're much more
not
like
very regular.
they're much more like jumbly and rough terrain, and like there's like pitting sort of. It looks like if you
Texture
sort of had
is
like
weird.
frothy stuff, and
Yeah,
then
it looks frothy.
settled. it
Higher
sort of looks
albedo
like that
as well.
And
I
yeah,
think.
the
so maybe
brighter.
a different kind of lava or
Yeah.
something,
That,
or
I mean,
more
yeah,
recent.
that's what the idea is.
Because the Mare, when we look at the moon, the dark from the Earth with the naked eye, the dark splotches are the Mare.
yeah, and
The
typically those are
so-called
relatively
seas.
smooth because they sort of flowed and filled
was
in
like lava.
It was running lava.
Yeah, running
Yeah.
lava.
And
Not like lava.
And
It
it
wa-
covered.
it was lava.
It was running lava that filled in giant ancient impact basins, covered up the craters that were created in abundance over the whole moon 4 billion years ago. And since there's been less cratering since then, they're smoother.
Right.
They're darker because of the composition. And then these imps are...
They're smaller than the mare patches.
Are they within a regular mare? Or are they adjacent? Or are they like within highland areas?
I think they're in the highlands. I thought they were in the highlands.
They're not
but
like part of a mare.
I don't know. They're distinctly different, though.
Okay. And they look frothy.
Frothy.
Rough.
There aren't as many impact
I think
craters.
they're in the mare.
They're in the mare?
Yeah.
Okay.
Yeah.
Okay. So
But
they
yeah.
believe that
So
these
just
grains come from
Not
those?
necessarily.
No, but imps are also evidence of younger volcanism. That's the tie. It's because imps seem to be younger. They don't have a lot of cratering on them, so
see.
that helps us tell that they're younger.
Okay.
And they seem to be like relatively newer volcanism as opposed
But
to some of the
125
other
million
things.
years ago.
And it would fall under that 125 million year category,
So
the imps. So
yeah.
but the range, because we have to use crater counting
This
to do it.
conflicts with my kindergarten level understanding of the history of the moon.
Same.
Which is that it all should have cooled off 4-ish or more billion years ago.
Yeah.
Because it's so small.
We say that all the time,
Yeah.
but
Right.
most of our data now tells us that's probably not true.
Yeah.
So
like
somehow
it takes longer for
something
things to
stayed
cool.
molten inside it for a
Yeah.
while.
And it seems to be like localized too.
For those,
So it could it have been the monolith from 2001?
I mean,
Sure.
Okay.
there's nothing proving it's not yet.
Yeah.
But maybe concentration of radioactive material providing
that's what-
trading.
That's often, especially on the moon, there's lots of weird patchiness of radioactive
Radioactive.
elements. And like we look at thorium and some other things and look
Glumpy
for where
stuff.
those are. Yeah.
Okay, cool.
Yeah.
You also have a moon story, Addie.
I do. Sorry.
I do.
So there's an interesting new paper from a group that does a lot of like geochemistry and modeling, and they that came out recently about. Wow, sorry, I wasn't on the right thing, and my brain hasn't switched to this topic yet. I was still
Something
thinking about
the
imps.
origin of the moon.
Yeah.
Do you want me to give you the trivia first while you get your brain?
Sure.
Okay. Burp.
That was
Does your brain shifting
brain
gears?
And I can read the
Gears.
abstract.
The trivia today is completely trivial. It is
Perfect.
random sci-fi fantasy trivia. It's a series of questions.
great. We haven't had something like that in a while. This seems nice.
Random sci-fi fantasy trivia.
Yeah,
That's
then
what you say
if I get
now.
it wrong, I don't feel bad.
Oh, you'll feel less bad than when you get the sort of basic astronomy questions wrong.
Yeah.
Yeah. Okay, here's your series of 4 questions. How many times in Star Trek, the original series, did Lieutenant Uhura, played by Nichelle Nichols, leave the ship?
Oh.
There were 79 episodes in the sort of canonical counting of episodes for the original series.
Okay.
How many times did she leave the ship? She's one of the main actors in the show, main characters in the show. Second, in how many episodes of Star Trek: The Next Generation, which ran for 7 seasons, unlike the 3 of the original series, did the character Q appear?
Well, I have an idea about that one.
Okay. In how many Star Wars movies does R2-D2 appear?
Oh my gosh, there's so many.
And then, what character has the most lines in the 6 Lord of the Rings movies?
Okay.
Is it most
Okay.
lines?
Most lines.
Okay. I
Yep.
think I
All right.
feel good about those.
Those. All right.
Some of them.
Okay.
Yeah.
All right.
Okay. So the moon, we were just talking about its recent history.
Yeah.
And how it's maybe more
It's
recent than we thought.
surprisingly
recent.
history.
But there's also a lot of folks who work on understanding the formation of the moon. So the ancient history of the moon is something we still have a lot of questions about because we weren't there, right?
Yep.
And so there's a newish paper out by Sosi, Nakajima, and Khan. I don't know if I'm saying those right. That does some really interesting matching between geochemical modeling and some like experimental observations, just sort of look at how the moon has evolved and how that like governs the structure of the moon. And Audrey was like looking through the paper earlier, and it makes some really cool plots that are like not they could be very nice like art on your wall. I feel like if you look at that plot,
Yeah, they're
it could
almost
be
like
some nice abstract art on your
retro.
wall.
Wall murals.
But they're actually like things that are looking at like what would the seismicity. So looking at like seismicity data and how that would change with different geology and crustal thicknesses and densities and stuff like that. So that actually is like science data, which is kind of crazy, right?
It's not just art.
So
these graphs are showing sort of the state of the interior of the moon as a function of depth and time.
Yeah.
So going down, and the radius of the moon is, what is it, 1,500 kilometers or something like that. And so for the Earth, we talk about a core, mantle, crust, which are compositional differences, and we talk also about sort of differences in, is it solid or is it molten? So there's a solid core and a molten core, and then et cetera. So is it similar sorts of things that they're talking about here with the moon?
Yeah, so they're looking at different compositions and trying to understand how intimately tied the sort of initial composition of the moon needed to be compared to the initial composition of the Earth, and like how those might have evolved. And how you can use like seismic data from the surface. So this is what we were talking about was like density waves and how you look at seismic data from the surface to like see what the structure is in the inside, how we might be able to use that of like upcoming missions and from existing seismic data that we have a little bit from the Apollo days to like make interpretations of that. And so I mean, it's a pretty long paper, but I think it's like an interesting. I saw it because I thought it was an interesting like overlap between looking at chemical composition and doing geochemical modeling, and then like seismic data and how we can sort of match some of those things up. That's just a little bit different than
putting all the pieces together.
Some of the other things we do, because they also have a lot in here about like what isotope tracers you would want to see if you were doing some compositional. If you could get rocks and look at the composition to like help you understand a little bit better what the evolution history was. And that tied to our previous talk about like sample return and things like that, really getting samples from the far side and like South Pole Aitken Basin and other areas would be really important because they sample at different depths in the moon and in different periods of time, basically in the moon's history, to help us constrain some of these things.
Yeah, I mean, I'm always impressed by what people are able to piece together from, it's like you have some weird observation and you sort of follow a thread. Okay, well, what does that mean? What are the implications? And typically there's like 700 different possible explanations for why maybe, for example, you would see a particular kind of glass grain in a lunar sample or whatever. But then you're like, yeah, but can I radioactive date it? Oh, it turns out it's 125. And then, but this could be impact. No, we'll do some experiments and discover that impact-generated glass has some particular characteristic, and we can rule that out. And then you sort of whittle these things down, pulling together frequently lots of different kinds of physics and stuff going on. And then it's like, from what appears to be such, insubstantial data, you can get some pretty impressive constraints on things.
And I earlier when you said they had samples and I was like, oh, is it glass beads? And that's because like one of the ways we have that we've gotten like evidence of water throughout the history is from little glass beads that we've found previously. And like this paper talks about like having little pyroclastic glass beads because those trap gases and other things that you can do. And then so like a couple of the so there's a lot of different things in the paper, and it's funny because they have like key points, and I think there's 10, which usually you try to make 3.
Right. Yes.
But it is really saying like, so they're looking at core formation and how the moon originally formed, and they talk about how you had to have had volatile depletion of the moon. So like we know that there weren't as many of the like light easily heated elements, volatile elements.
I mean, if we go back to like the main idea for how the moon formed,
giant impact
onto the Earth, right? Yeah. And when you have a giant impact, things get super hot.
Yeah. But a lot of times when you have a giant impact, a lot of the material for like the moon comes from the precursor. So you probably have had to have had a volatile depleted precursor. additionally. So there
okay.
weren't as many volatiles there, they say. But you can
interesting.
also look at some of those isotopes. So they were looking at tungsten and something else to look at to get a little bit more information about like how much came from the Earth's composition versus the Moon's composition, which is something we still don't really.
Right.
There's sometimes a lot of discrepancies still between how we model it and what we measure. So they're trying to get at that a little bit better. But the last key point was there's no one dynamical model that satisfies all geochemical and geophysical properties of the Moon.
Interesting.
So they're just saying they still have to keep working.
Right.
So that's nice.
Yeah.
Well, that's good. They can point to that.
In their proposals.
Yeah.
Yeah. The precursor impactor is not a thing that we've observed, right?
No.
It's just is named Thea.
Yeah.
And Mars-sized, which
Yeah.
means about
Probably.
1/10 or 1/8 the mass of the Earth. So a planetary object,
Yeah.
but pretty significant. And
Yeah.
cool.
It's interesting. Yeah, it ties it. I don't know. This paper, I was like, oh, this is an exciting paper. And then I was like, oh, there's so many things to talk about,
There's
as
a
you can
lot.
tell from my rambling sort of here. But
But it is also cool because it has predictions as well. So
Yeah.
it is really good if you are trying to put a mission together, or if you have a question, you want to know how to answer it. I like that they're like, they
these
kind
things
of,
will be
yeah,
useful
like-
to get.
Yeah.
Identified some, here are the steps, here are the measurements. we gotta deal with.
which is
Yeah.
always great in a paper.
Yeah.
Well, I think I promised Top Quark on this
Yeah.
episode.
Sorry, everybody.
And Top Quark was unable to join us. But I spoke with Top Quark earlier, and
He's alive?
He's alive and well, and hopefully will be with us on the next episode. We tested our sound connections and everything worked out great. So we have a somewhat astrophysical topic in Top's honor.
We do.
For our last topic.
We're dipping our toes back into
Back
more
outside the solar
astrophysical topics.
system, right? So this is about a new study looking at over 100,000 stars from data from the TESS, the Transiting Extrasolar Satellite Survey, something like that.
Exoplanet?
I think it's exoplanet.
Satellite Survey, Stellar Survey, Satellite something. It is a satellite,
Yep. Survey satellite.
could be.
Sure.
TESS is monitoring lots and lots and lots and lots of stars for changes in their brightness, which would be due to transit of an exoplanet. So it's an exoplanet hunter. The same process as Kepler, but a different style of mission, looking at stars for a shorter period of time, but looking at more stars.
Yeah.
So it's got a different
So
kind
many
of
stars.
Yeah. So the question that's studied in this paper is because there's lots of different kinds of stars in the galaxy, and there's a property that we use to identify sort of an age of the stars called the metallicity. And again, we've teased astronomers about this before.
Silly astronomers.
In astronomy speak, a metal is anything that isn't hydrogen or helium.
Yep.
In this particular
So silly.
in this particular study, they're actually using an actual metal, iron,
Yep. As a proxy.
as a proxy for how much non-hydrogen helium stuff there is. And,
And like often when we talk about the metallicity of a star, it is an iron ratio basically.
yeah, but it could, sometimes
be-
they're looking at like oxygen or carbon.
You could even
because
do like lithium.
if you start with at the beginning of the universe, you have essentially only hydrogen and helium, and the heavier elements are made in the interiors of stars.
Yep.
And the only way that gets out is those stars have to do their thing and blow up.
Yeah.
And
Do
send
their
that stuff
thing.
out into
Spit
the
stuff out or
galaxy,
blow up.
and then you make a new star that's got some of that so-called metals in there. And so to have planets, you need that stuff, right?
The
you can't make
sun
a planet just from hydrogen and helium.
Is like 1.1% metals
yeah.
for reference.
So not a lot.
Not a lot.
Right.
It's not
so
very
still
metal.
mostly. But it's not a metal poor star.
No.
And so
There's
this
stars that have
study,
less.
which by Kirsten Boulay et al., is looking at metal poor stars. And it's trying to figure out, as we sort of reduce the abundance of the non-hydrogen, non-helium stuff in a stellar system. So, you got the star, and we can figure out the composition of the star from the spectral features there. And then there's a relationship between what's the star made of and what's all the stuff around the star that you make planets from. And you need to have some of those so-called metals to make the planets. So they're like saying, okay, how far down, if we turn the metallicity down, do we keep making planets? And how far do we go? And, there's a long story because there's lots of different kind of planets. Are you talking about Earth-sized planets, talking about Jupiter-type planets? Anyway, all of them require that non-hydrogen stuff, even though Jupiter is mostly hydrogen and helium.
Yep.
It can't get that hydrogen and helium without having a sort of rocky, metallic, icy core to begin with. So they looked at like 110,000 stars.
Just a few.
Is that enough?
That's some
It's
good
interesting.
statistics.
So, I mean, that's a good question. Like, how many stars is enough?
That has to be enough.
It is.
Okay, good.
But it's not enough by like a factor of 1,000.
No?
Because they, in their search, they're like saying, okay, most stars you look at, you don't expect to see a planet. Because with this survey, this transiting exoplanet approach, the planet's got to be in close if you're going to see it with tests, and it's got to be lined up so that it cuts across. So most of the time, you're not going to see a star anyway.
Right.
So they did control samples, all that stuff. They predicted that they would see 68 super Earths in their sample.
Yeah, and like part of that is they look at all of those stars, but then as we've talked about for other surveys, you like
Have a control.
but then you also like have to limit it and you throw out certain things
Right.
and you say we're just going to look at this type of this
Right.
from those 100,000 stars. You knock down.
They're like, we're not looking at red giants. We're not looking at stars with weird gravity. We're not looking at stars that are too faint because the signal is too hard.
Yeah.
They did all sorts of careful things to make sure that they had their correct, sample where they would see it, and then they do the a clever thing of like randomly injecting artificial signals into the data and then making sure that their data analysis process finds those artificially injected signatures to confirm that their data analysis does find these things.
Yep.
Anyway,
What do they find?
They predicted 68 super Earths.
Okay.
And they found, drum roll, 0.
No.
Oh no.
In low metallicity stars.
What is low metallicity? So
Less than the sun, but so like
the
less
sun
than a
has, like-
percentage.
okay,
It's-
like
yeah,
a
I
percent
mean,
of a percent.
The value is less than minus 0.5 in this bracket representation, which is a logarithm of the relative abundance.
A negative percent?
Because it's a log.
It's a log.
It's not a percent.
It's the exponent
Oh, it's a log of
the iron abundance relative to the
hydrogen
solar
abundance. Solar
iron
hydrogen.
relative to hydrogen relative to the solar system. So yeah,
It's a relative
So-
abundance that's not a percent, but it's a negative because it's a log, and
it's tied to the
it's
sun.
referenced
the
to
reference to the sun.
reference to our,
Okay,
yeah.
yeah.
So
Cool.
so that means, what does that mean? It means that what are the
There's
stars
no
that have low metallicity? It's stars that formed a long time ago.
Yeah,
And so
generally, because as you
a long
form
time
new
ago, there weren't many metals.
Yeah, because you started with hydrogen and helium. It takes a while to form the new stuff. And then as you have new stars forming, they incorporate metals. And so typically over time, stars tend to become more metal.
Right. So the sun formed 4.5 billion years ago. The galaxy had been around for 13 or 14 billion years at that point and had been blowing up stars. Well, not at this point. So 9 or so billion years at that point. So for 9 billion years, this galaxy had been making stars, making heavier elements, metals, blowing up that the sun could incorporate.
Yep.
But if your stars that formed at the beginning of the galaxy didn't have those raw materials available, and if they're still around, that means they're small stars because massive stars blow up,
Yep, they're gone already.
right? So
Okay. So
this
they're
says
little-
a very low
smaller stars.
probability, lower than we would have previously guessed by extrapolation for old and therefore these smaller early. Now, of course, there's a lot of small stars that are new, like you can make a small star now. But these old
can make
stars,
one.
which are primarily
can make one.
smallish stars,
Yep.
are not likely to have. And then there's all sorts of cool stuff, which, I won't go down the rabbit hole any further than I already have, but the metallicity also ties into like what is the physics going on in the disk where the planets form, because it controls how the radiation from the star gets processed in the disk, whether there's turbulence, whether the disk settles down to make a dense enough plane for things.
You said you weren't going to get into the.
I'm not getting into it. I'm just
teasing.
listing the things that I'm not getting into.
All of this stuff is really relevant for planetary rings, also.
That's right.
So shout out to the sponsor.
Yeah.
So why did they expect 68? If it makes
based
so
on
much
an extrapolation,
Based on extrapolation from other data.
So, like, if metallicity wasn't a thing, if you just took a look at the trend from the more metal. So, as it turns out, Kepler, which is where most of our planets have been seen, looked at stars that are higher metallicity.
Just generally?
Well, I mean,
like
sunlight.
intentionally?
They're sun-like stars.
Oh, that's true. Yeah.
So they're nearby. There aren't a lot of metal-poor stars nearby. They looked in one direction. It just turns out their sample was stars like the sun.
Right.
But there's some range of metallicities, and if you extrapolate that, you would get to 68.
Got it. Okay.
In this low metallicity range.
Got it.
And what they call it a metallicity cliff, which is as you go to the lower abundance of these heavier elements, at the certain level, the number of planets drops like off a cliff.
And this paper is mostly focused on super Earths also.
Yes.
So planets that would be super Earths.
Right.
So.
Right.
But it wouldn't really matter for the it could be just anything that's detectable.
You couldn't, if you started to extrapolate this to like Earth-sized planets, then you might not be able to make as strong a statement.
Sure, I guess I more meant in the other direction.
It could be giant stars or giant planets. And things like that.
Like Jupiter's and
I think they use it for super Earths because we're interested in Earth massy stuff. But I actually don't know why this study limited it to not having giant
like
planets.
hot Jupiters. Yeah,
I don't actually know.
like that. Yeah.
But either way, they found nothing.
I mean,
it wouldn't
they
have...
found no super Earths, and that's specifically what they were looking for, with orbital periods between 1 and 10 days.
Gotcha.
Yeah.
So they were looking at this is what we were talking about
I'm
before.
all cut up now.
Like Addie was saying, you got to throw out this, you throw out that.
Yeah,
They're like, here's the specific question, and that's what they found. Here's another specific question. How many times in Star Trek, the original series, did Uhura leave the ship out of 79 episodes?
3.
5.
Audrey hits it on the nose. That's why I'm impressed with both of you for recognizing how much she was trapped on the ship.
Yeah, she didn't go off the ship.
She didn't have many
very
opportunities.
Much. She did a dance one time when she did. Oh, that's in the movie. That's in the movie.
Yeah.
The
How many
fan
episodes
dance?
of Star Trek The Next Generation does Q appear? As 200 and some episodes.
I think it's like 5.
7.
Addie gets this one, it's 8.
Okay.
So, yeah, good for you.
Okay.
And how many Star Wars movies does R2-D2 appear?
How many Star Wars movies are there now?
Can I just say all of them?
11.
No.
You can
I mean,
say
you could.
there are 11.
Okay.
I'll tell you there are 11, so you can say 11.
There are 11 Star Wars movies. So you're counting Rogue One and
Solo. Plus the 9.
There's the Rolly one that isn't R2-D2.
BB-8.
Yeah, so that one
not
that doesn't
R2-D2.
count.
There's
boy.
there are many robots that aren't R2-D2.
I feel really bad for you right now.
Droids.
In Latin America, he's called Little Arthur.
I didn't know that.
Why is he called that?
R2-D2 is like Arturito.
Yeah.
Like Little Arthur.
Little Arthur.
That's
in the
adorable.
original, I don't know what they did after sequels started coming out, but when the first Star Wars came out in 1977 in France, Darth Vader was called Dark Vader because the TH is not in French.
It's not a
that
thing.
sound is not a
A
thing
lot
in
of
French. So it's
languages.
just like Dark Vader because he was
Very hard
dark.
for Riley too.
And they didn't know it was going to be like, now we have to have Darth Maul and everything.
Yeah.
Oh, that doesn't work. Just kidding.
5. 7.
10.
Oh wow! All but one.
All but Solo.
Oh, so now is it? Oh, I was gonna say now it's which one is it not in?
Oh, I should have given you that. Sorry. Which
I was gonna
character
guess Solo.
has the most lines in the 6 Lord of the Rings movies? So that's one movie for each of the
can't even
giant
think
books
of
and 3 movies for the small book.
Yeah,
Samwise Gamgees.
my gut is saying Gandalf, and I feel like that has to be right. But
He's a thread.
You also
that
didn't say if it was
connects.
extended or which extended version.
Books.
No. Movies.
Oh, you said movies. Oh,
Movies.
that's true.
Yeah, so I feel like it's Gandalf.
Okay.
I feel like it's definitely
You're
not
going
Samwise,
Sam?
though.
Yeah.
It is Gandalf.
Yes!
That's a good.
If I got that wrong, I would have been
Fewest?
so mad.
Samwise.
Fewest.
Lines.
I mean, there's like a million characters that
That's
don't have
true.
any lines.
Yeah.
Duh, like I have 0.
Yeah.
Legolas, and it's true. I don't even
Of
really
the
know
main
what that means.
characters,
It's probably
like
Legolas
the
has the
fellowship people. I
Yeah.
don't know. Yeah.
of the Fellowship who has the fewest.
Okay. Yeah.
I
Okay.
agree. That wasn't an official question, so it doesn't
Okay.
count
That's-
against you in the
okay.
scoring. Okay.
Don't add us in the comments.
This will not be
Okay,
counted
good.
in the official
Can you
trivia
imagine?
scoring.
I can't.
While it may have felt like falling off the Metallicity cliff, it was just another episode of Walkabout the Galaxy.
Be sure to follow us on Instagram and YouTube. You can contact us at wtg@ucf.edu.
Our theme music was composed by Richard Jerusik. Production assistance is provided by Logan Basinger.
I forgot to say thanks to our listeners in Middle Earth and Real Earth.
In the middle of the real Earth.
Stay safe. I'm Josh Caldwell.
I'm Addie Duff.
And I'm Audrey Martin.
We're the astroquarks signing off until the next episode of Walkabout the Galaxy.
Thanks, Katie.
Beep beep. Boop boop.